Hello and welcome to another Calculus Center math video. Today we're going to be approaching the following volume problem. Suppose that a solid is formed using the shaded region shown below as a base and square cross-sections perpendicular to the x-axis. Our goal is to set up an integral that could be used to calculate the volume of this resulting solid. So I don't know about all of you, but the first thing I want to do is visualize this region a little bit more. Because once I visualize something, it becomes easier to work out the computations for it. So what do we know that will help us visualize? Well, we know that we have square cross-sections, and we know these cross-sections are perpendicular to the x-axis. So the first thing I've done is I've actually modeled this situation on a piece of paper. So I have the region drawn here, and I've used sticky notes to draw in my square cross-sections, right? So these cross-sections are popping out of the page, or out of the board, and they are also perpendicular to the x-axis. So we have square cross-sections popping up out of the page, perpendicular to the x-axis. I'll also provide a little bit of a picture here that will help you visualize this a little bit further. It's not the same region that we're dealing with now, but it gives you an idea of what these volumes would look like. All right, hopefully those pictures gave you a feel for what this volume is actually supposed to look like. I've drawn in a rough sketch of a couple of cross-sections that are squares perpendicular to the x-axis, and it's kind of hard to tell, but remember, these are sticking up out of the board, okay? So just like the model you saw with the sticky notes, these cross-sections are coming out of the board. Now, how do we approximate the volume of this region? Well, this is exactly how we would approximate the area of a region bounded between a function and the x-axis. Remember, in order to do that, we used a Riemann sum, and we added up the areas of a bunch of rectangles. Well, we're dealing with volume, which is in 3D, so we need to use a 3D variant of those rectangles, and, well, a 3D variant of rectangles would be rectangular prisms. So let's sketch our cross-sections that we had very roughly. And now we want to add a third dimension to these. So I'm going to add a little bit of thickness to each of these. I'll call it a dx thickness. A dx thickness for that as well. And a dx thickness for this too. So if I wanted to look at one of these prisms and label it a little bit, I've got the length here, the width here, and the height is the thickness of dx. Also, I'm able to find the area of this cross-section as well. I'm going to write it as a of x because the area of one of these cross-sections is going to depend on the x value that the cross-section is at. For example, when x is equal to 3, the area of this middle cross-section is different from when x is equal to 4 and the area is much bigger, right? So area depends on the x value we're at. So now if I were to find the volume of all of the prisms like this, I could add them all up and I'd get an approximation of the volume. So volume is approximately the sum of the volumes of the prisms. So now the question is, how do you find the volume of a prism? Well, the volume of a prism is equal to length times width times height. And we know that length times width in our picture is just the area of the cross-section, which we've called a of x. And then the height of each of these prisms is going to be dx. So to find a volume of a single prism, we have its area, the area of the cross-section, the area of the base of the prism, in other words, and we want to multiply by dx, the height of one of these prisms. So now if we added up all of these volumes together, we get an approximate volume of the region we care about. We want the exact volume though, and in order to get the exact volume, we're going to have to use more prisms, right? Just like we used more squares in order to get a better approximation of our area, we're going to use more prisms to get a better approximation of our volume. And we don't just want a better approximation, we want the exact value. So in order to do that, we're going to have to take a limit as the height of each of these prisms tends toward 0. So in other words, we're going to take the limit as dx goes towards 0 of the sum of these volumes. And when we do that, just like when we took the limit as the thickness of our rectangles in a Riemann sum went to 0, we'll end up with a definite integral. So the volume that we want, the exact volume of our region, is going to be the definite integral from a to b, the starting x value of your region, and the ending x value of your region. And we're going to integrate the formula for the volume of each of these prisms. The area of the cross-section times dx. And this formula is what will allow us to calculate the exact volume of this region. All we have to do is plug in what is our a in our situation, what is our b in our situation, and what is the function that will give you the area of our cross-sections. Okay, so now all we need to do is use this formula in order to find the volume of this exact region. Great. So our cross-sections are squares in this case, and we know the area of a square is just the side length of that square squared. So we just need to take a look at our cross-sections, which we have over here, and look at what the side lengths are going to be. You'll notice that these side lengths I'm drawing in green are just given by the distance in between two functions, right? The distance in between this top function of y equals 4 and this bottom function, which is the brown one, which is called f of x. So in order to get a side length of one of these, I need the distance between those two functions. And well, the distance between these two functions is given by 4 minus f of x. So this is my side length, and I have to square it. Okay? So now we're off to the races. I can calculate volume by taking the definite integral of the area of my cross-sections with respect to x, and I want to integrate from the x value that begins the region I'm dealing with to the x value that ends the region I'm dealing with. So my region starts when x is equal to 2 and ends when x is equal to 4. So I integrate from 2 to 4. A is 2, b is 4, and then I'm done. We've set up the integral, and you could evaluate this integral if you knew what f of x was in order to get the volume of this region. That's really all there is to one of these problems. Once you know this formula, all you need to figure out is what is the area of one of my cross-sections, and then you plug it into the formula. Let's do another variant on this problem. Let's do the exact same problem. We're going to be dealing with the exact same region, but now we want to use cross-sections that are semicircular and perpendicular to the x-axis. Again, these are going to be coming out of the page, but this time our cross-sections are going to be semicircular. So I'll draw a few in. All right, I've drawn in a couple of cross-sections. Remember that these are coming out of the page, even if it doesn't quite look like it from my sketch. But remember, your sketch doesn't really have to be perfect as long as it gives you an idea of the situation. So now we remember that in order to get the volume of a region, you want to integrate the function that gives you the area of the cross-sections from the starting x value to the ending x value of the region. All right. So the area of a semicircle is 1/2 pi r squared. So our function that will give us the area of our cross-sections is going to be a little bit different. It's going to be 1/2 pi times whatever the radius is squared. Okay? Well, the radius on our cross sections is going to vary as x varies, right? So here's a radius in orange, here's a radius, here's another radius. You get the idea. Each of these radii is going to vary as x varies, but basically the idea is we want to find this radius. Notice that this is exactly half the distance between y equals 4 and this bottom function f of x. So we're just going to take half of that distance, which is exactly half of the side length that we had before for our squares. So we want to take 4 minus f of x. The top function is y equals 4, the bottom function is f of x, and we want to divide by 2. There's a lot of 2's in this problem. Don't forget any of them. They're all very, very important, lest you end up with the wrong answer. Okay, so now we can find the volume. The volume is equal to the integral from a to b. We know a is 2 and b is 4 from the previous problem. And now we just integrate the area function for our cross sections, which is 1/2 pi 4 minus f of x divided by 2 squared. And this is all with respect to x. So with that, we have our volume, and we're done with yet another problem. Notice that all these problems boil down to is recognizing which cross-section shape you're dealing with. So in this one we had semicircles. Noting what the formula for the areas of these cross-sections is, and then writing the area of these cross-sections in terms of x, using your sketch ideally. Once you've done this, you just plug a of x into your integral, figure out what the upper and lower bounds for your integral should be, and you're on your way. That's it. So you might want to practice more of these problems. They're pretty tricky at first because they're hard to visualize. So practice more of these, rewind this video if you need to, and of course, if you're struggling after that, feel free to come on down to the Calc Center. There'll be somebody there to help you. In the meantime, happy math, and we'll see you around the Calc Center. Goodbye.